So last class we talked about vectors. We talked about how we describe vectors in X and Y component language and in magnitude and direction language. And we talked about how we add vectors together for different cases, different examples. Today's class, we're going to get back to a bit more physics and a bit less mathematics. And we're going to talk about what we call projectile motion. Now, classic examples of projectile motion are, for example, if you throw a basketball, throw a baseball, you kick a football. Those are all classic examples of projectile motion, a object, a body that's thrown or kicked and is moving through space in time in a two-dimensional path. The object will be going, say, left to right and up and down. And so that's two-dimensional motion. That's projectile motion. So there's a long history of studying projectile motion. There's a long history of wanting to understand projectile motion. And a lot of it was related to hundreds of years ago, military programs. So if you wanted to fire a cannonball, for example, from your favorite castle or from your favorite ship, you wanted to predict where the cannonball would go. You want to hit the target. And so that's a problem of understanding the motion of projectiles. That's a problem of projectile motion. And so there was a lot of interest in projectile motion. And what we'll see in today's class is that the breakthrough in projectile motion is due to somebody we met in a prior class, Galileo. He made the breakthrough in falling body motion, and he also made the key breakthrough in projectile motion. So we're going to follow some of his work. Specifically, we're going to begin with a famous experiment that he conducted comparing falling body, one-dimensional motion, with projectile, two-dimensional motion. And out of this experiment came a way of understanding projectile motion, which is in two dimensions, and it's a complicated path that the projectile follows. What he figured out was you could understand that motion, that complicated motion, by thinking separately about the horizontal and the vertical components of the motion. And by thinking about the horizontal and vertical components of the motion, he kind of exposed a simplicity of the motion that was hidden in the more complicated two-dimensional motion. Okay, so let's redo his famous experiment. So I'm going to change to a little video where we'll see me repeating his experiment. And the experiment, as I say, compares falling body motion with a projectile motion. And specifically, what it involves is two steel balls sitting on a platform. One on the left of the platform, one on the right of the platform. And one of them is just dropped from the platform, the one on the right. And the other one is pushed from the platform, the one on the left. So one of them, the one that's just dropped from the platform, just falls straight down. That's a falling body. The other one, which was pushed, moves through two dimensions, both right to left and downwards. And so that's projectile motion. And so we can compare what I call the falling body with the push body. We're comparing projectile motion with ordinary falling motion. So I hope you can see my my canvas page, and I'm going to play this little video here. So just to point out a few things, upstairs here is the platform. And I'm going to put a steel ball on the left-hand side and the right-hand side of that platform. And by releasing a lever, one of the balls, the one on the right, will just be dropped straight downwards to this metal sheet. And the other ball, the one on the left, will be thrown off, pushed off the platform towards the left-hand side, and pushed off with enough velocity that it will strike this metal sheet over here on the far left. And we're going to compare they're going to be released, pushed, or dropped at the same time. We're going to compare the times that they strike the bench, strike the metal plates. And you'll be able to compare that because you'll hear them hit the metal plates. And you'll either hear one strike if they're simultaneous, or two separate strikes if they're at different times. So these are the two steel balls that I'm putting on the platform. And the platform has a lever that drops one and throws the other. And hopefully there you heard just a single hit as the two balls simultaneously hit the metal plates at the same time. I'm going to play it again, but I'm going to slow it down here if I can. Okay, so I hope you agree that, well, I've dropped one metal ball, the one on the right. I've thrown a second metal ball, the one on the left, and they followed very different paths. One was one-dimensional, straight line, falling body motion. The other one was two-dimensional, curved, it's a parabola, projectile motion. But they struck the metal plates at the same time. They left the platform at the same time, and they struck the metal plates at the same time. And that's an experiment that Galileo did, and that's an experiment now that we've just repeated. So I'm going to go back to my slides now, if I can. So we've repeated this falling body versus push body experiment, and we've discovered that the two objects fall the same distance in the same time. And here's a little graphic showing that. This time the falling body is on the left, the projectile is on the right, and the horizontal red lines, they mark interval time intervals as the objects are dropped from the platform. So the first red line is a second, the second one's 2 seconds, third one's 3 seconds, fourth one's 4 seconds, and then 5 seconds. And you see in this graphic, like we saw in the demonstration, that although the paths followed are quite different, if you just focus on the vertical motion, you see that both spheres cover the same vertical distance in the same time. And so that was an important conclusion about the vertical motion. The two objects are observed to travel the same vertical distance in the same time, which means that they must have identical downward gravitational accelerations. Their pull to Earth under force of gravity, due to the acceleration of gravity, is identical for the straight line falling body as it is for the curved path of the projectile motion. And so that's an understanding of projectile motion and falling motion that is key to understanding those two types of motion. The other thing we can say is something about the horizontal motion. And the key thing about the horizontal motion is that during the fall downwards from the platform to the floor, the two spheres, both the drop one and the falling one, carry on moving horizontally, continue to move horizontally with whatever their initial horizontal velocity was. So for example, for the falling body, its initial horizontal velocity was 0. And so it continues to fall with 0 horizontal velocity. It doesn't move left or right at all. The projectile, that had a non-zero initial velocity. And so as it falls, it continues to move with that non-zero horizontal velocity. It doesn't get any faster, doesn't get any slower horizontally. It maintains that horizontal velocity. So they're both continuing with their initial horizontal velocities, whether they're 0 or non-zero, which means that the acceleration in the horizontal direction is actually 0. They don't speed up horizontally, they don't slow down horizontally, they don't change their horizontal motion. They have 0 horizontal acceleration. And so that's the second key fact about the falling body and the projectile as they move from the platform towards the ground. Okay, so here's an important slide that kind of summarizes what I've tried to just describe, is that the key to understanding projectile motion is not to think about the complicated two-dimensional path or trajectory of the projectile, but rather to understand projectile motion, we break that projectile motion down into two parts: the vertical motion, the horizontal motion, a one-dimensional vertical motion and one-dimensional horizontal motion. If you think about those two parts separately, the one-dimensional vertical motion, if I can get my pen going again. Oh, what did I do there? Oh, I lost the entire screen. Sorry. I got to get back to where it was. The key thing about the projectile motion in understanding it is to break it out into simple one-dimensional vertical motion in which you have an acceleration that's 9.8 meters per second squared, the acceleration of gravity, and a simple horizontal motion, one-dimensional horizontal motion with an acceleration in the horizontal direction that's 0. And the complicated two-dimensional motion, the parabolic path of the projectile, is simply the superposition, the addition, the combination of these two simple motions. And so that's how we understand projectile motion. And I'm not trying to advertise this here. If we had horizontal and vertical eyeglasses that you could put on the vertical glasses, you just see the vertical motion. Put on the horizontal glasses, you just see the horizontal motion. Then you'd realize underneath that complicated two-dimensional path just how simple the vertical motion is, just like a falling body. Just how simple the horizontal motion is. It's just an object moving with constant velocity. And so we don't have these glasses, obviously, but imagine having these glasses, and that's the way to understand, comprehend projectile motion. Okay, I want to show you one more demonstration to convince you that the motion of a projectile in the horizontal direction is a constant speed, constant velocity. So the motion of the projectile in the vertical direction is under the acceleration of gravity, but the motion of the projectile in the horizontal direction is with just constant uniform velocity. And so I'm going to show you a second demonstration here. What we're going to do is we've got a cart in which there's a ball, a projectile. And I'm gonna eject the ball from the cart as it's moving. The ball, when it's ejected from the cart, carries the same horizontal velocity as the cart carries when it released the ball. So initially, I've written it down here, the horizontal velocity of the ball, which I called V0 for initial velocity, X for the horizontal component, and B for the ball, is the same as the horizontal velocity for the cart initially. So I've got V0 X, the horizontal motion of the cart, and C for cart. So they start out with the same horizontal motion, and as they travel from the left and right, we'll see this, they continue with that same initial horizontal velocities. The ball and the cart do. It's not changing, despite their very different paths. And then finally, we'll see that the projected ball lands back in the cart because they traveled the same distance from left to right, because they had the same horizontal velocities from left to right. And that fact that I can catch the ball in the cart after projecting the ball from the cart proves that they both had the same horizontal velocities, that they continue to have that initial velocity in the X direction for the ball, initial velocity in the X direction for the cart. And so let's take a look at this this demonstration. So I've got to stop sharing this guy. And I'm going to share a second video. And here we are. So I hope you can see the second video now. And I'm going to play this one. So this is the cart, and I'm just showing you in a very dramatic fashion that it's got wheels on the cart. And now I'm showing you that the cart with the wheels on the track glides smoothly left to right. Now I'm gonna slow down the video because I'm gonna fire a projectile, a ball from the cart as it moves from left to right. I'm gonna kind of play catch with the moving cart and demonstrate that the projectile, the ball, has the same horizontal velocity as the cart. So again, it's like a comparison of straight line motion and two-dimensional projectile motion. So I hope you saw that. The projectile leaving the cart and then returning to the cart, both having moved horizontally from left to right um, due to their initial velocities, but both moving with the same constant velocity. They're not accelerating in the horizontal direction. So this time I'm going to just allow it to come to a rest, and you'll see the ball just fired straight up and straight back down. So there were no tricks there. It's just that when I fire the ball, that ball has the same initial horizontal velocity as the cart and the ball maintain that initial horizontal velocity, and therefore the ball is caught by the cart. Okay, so now I'm going to attempt to go back to my overheads. And let's move on to the next slide. So we really done a couple of experiments. We really established this simple interpretation of two-dimensional projectile motion as vertical motion under the acceleration of gravity and horizontal motion with zero acceleration. And now we're going to use that understanding, those key thoughts to solve some problems. So in this question that I'm going to work through, we're told that in the first demonstration, so not the last one, but the first demonstration, when I released the projectile from the platform, its initial horizontal velocity was 0.6 meters per second. And its the height of the platform was 1.1 meters. And so those were numbers I just took from that particular experiment. That's the experiment we did. Oh. I'm trying to use the annotation again, and it really does test my coordination for some reason. Okay, so we're going to answer several questions. So in this situation of the projectile, here it is in red, how long does it take to hit the ground? How far does it travel horizontally? And what's the ball's speed or velocity at that moment it hits the ground? Three sort of simple questions, obvious questions, that we can now understand through our deepening understanding of projectile motion. So let's see if we can do this, which mainly means, can I control the drawing pad? Okay, so first question, how long does it take to fall? How much time elapses between leaving the platform and striking the ground? And the way that we're going to figure this is by thinking only of the vertical motion. Not going to think about the horizontal motion at all. We're going to think about the initial height of the platform. We're going to think about the initial vertical velocity of the ball. We're going to think about the acceleration vertically, and in that way solve this problem. So the first thing I did over here on the left-hand side is I made a sketch of what I know and what I'm interested in about the vertical motion. Okay, so let's go through these things that I wrote down. The red arrow is the vertical motion of the ball. It's of course, following a curved path, but I'm ignoring horizontal. I'm just thinking vertical. So here's the vertical motion. It started on the platform and then struck the ground. So I made a couple of choices here that are just choices. So you could solve this problem a different way, but I chose to call the location of the platform, y naught, the initial position, that's 0 meters, and the final position when it strikes the ground plus 1.1 meters beneath the platform. That means I'm calling downwards as the positive direction. Upwards would be a negative direction. And that's a choice. So these are my initial and final coordinates. This is the acceleration of gravity, which is downwards. And because I've chosen down as the positive direction, it's plus 9.8 meters per second squared. This is the initial velocity in the vertical direction. Now, the projectile was pushed with a horizontal velocity, but it has 0 initial vertical velocity. So that's that quantity. I actually don't know yet, we're going to figure this out later, what the final vertical velocity is, but it has some. What we're interested in here is how long does this projectile take to reach the ground? And we're gonna solve it by thinking of this picture, which is really isolating the vertical motion, thinking only of the vertical motion. It looks just like a falling body here. Okay, so here's my solution. I went back to my old friends, 3 old friends, the equations of motion. And I looked at those equations of motion. I said, I want to figure out the time that it takes this projectile to hit the ground. Who can help me? And this equation here that tells you the displacement of an object under constant acceleration is the one that can help me. Because I know the displacement, I know the initial velocity was 0, which makes things simple. I know the acceleration, it's the acceleration of gravity. The only thing in that equation I don't know is the time taken. And so I can use that equation to solve for the time taken. So I'm going to take this guy here, and I'm going to rearrange it for the unknown time in terms of the known displacement and acceleration of gravity. So I removed this term with the initial velocity because it's 0. And then I multiplied by 2. I divided by the acceleration, and I took the square root to isolate the time. We want the time here. And then that gave me this equation here, that the time taken is just twice the displacement divided by the acceleration, and take the square root of that. The displacement was 1.1 meters. The acceleration was 9.8 meters per second squared. I took the square root of that. I got just under half a second. And that's the time taken. And if you think about it, that's quite an achievement to be able to calculate that. You look at that projectile motion, you say, this is a complicated curved path. It's a parabolic path, whatever is that. But by separating out that complicated motion into vertical, horizontal parts, you can straightforwardly treat the projectile like we treated a falling body and figure the time it takes to hit the ground. And that's what we just did. Okay, what was the second question? I've forgotten. We're going to find out when I go to the next slide, if I can. Oh, there's a comment down here. So note, when I did this problem, I chose downwards as positive direction. You could do the same problem choosing upwards as the positive direction. You would get the same time. So if you want to try that out, feel free to do so, obviously. But the time that it takes can't matter whether you choose up or down to be positive. in either case, as long as you make all your quantities consistent with that choice, your speeds, your displacements, your accelerations, consistent with your choice of whether up or down is positive, you'll get the same time. I actually did the other choice on this slide for you, but I'm not going to talk about it, but you can take a look at it. It's like a free slide. Okay, how far did the object travel horizontally? Let's try and answer that question next. Again, you look at it and say, oh, that's a hard question. This is complicated curved path. It's a parabola. I don't know what a parabola is. How am I going to figure this out? You do it by saying, I'm going to step back and I'm going to think of either the horizontal or the vertical motion to solve the particular question. In this case, we're going to think about the horizontal motion. So horizontally, the motion is very simple, very straightforward. Horizontally, the motion is just motion from over here on the left to over here on the right. This red line is the horizontal motion of the projectile with constant velocity, with zero acceleration for that time interval of just under a fraction of a second. Sorry, just under half a second. And so I drew the horizontal motion, the red line here, and then I added on the picture the things that I know and the things that I'm interested in. So things I know, for example, I know there's no acceleration in the horizontal direction, ax equals 0. I know the time taken, we just figured that out, it's 0.47 seconds. I know the initial velocity, 0.6 meters per second, we're told it in the question. And I know because there's no acceleration, that's the final velocity too. I'm going to call the initial location that we start at, I'm going to call that x equals 0. So that's my initial position. And we're going to find out what the final position is, how far we went. And so again, this is a problem of applying the equations of motion for constant acceleration motion. Zero acceleration is a special case of constant acceleration motion. And we're going to apply those equations of motion to solve for this distance traveled, this displacement. So let's do that. And here's my solution. So again, I thought about my old friends. I've got 3 friends. The 3 equations of motion. I mean, I've got more friends than that, but 3 equations of motion friends. And the one I'm going to use to solve this problem is the same one, really, but for the horizontal motion rather than vertical motion. It's the one that tells you that the displacement for your trip is the sum of these 2 pieces, one depending on the initial velocity, one depending on the acceleration. And since I want the displacement for the trip, and I know all the quantities on the right-hand side, the initial velocity, the acceleration, the time elapsed, I can figure this, this displacement. And a key thing here, which makes it very simple, if you look at that equation, is we've got 0 acceleration. So if we got 0 acceleration, this second piece goes away. And the displacement is simply the product of the initial speed times the elapsed time. So that's what I've written out down here. The displacement is going to be the initial speed, v0x, times the elapsed time. That's 0.6 meters per second times just under half a second, comes out to be 0.28 meters. And so that's how you solve the horizontal distance traveled. We didn't have to worry about the complicated parabolic path. We just had to think about the horizontal motion to find the horizontal distance. Again, I made a choice here. I chose to the right as being the positive direction. So my initial final velocity is positive. That gave me a positive answer for the displacement, 0.28 meters. If you had made the opposite choice, the left being positive, then your velocities would have been negative and your displacement would have been negative. But both are the correct answers given your choice about which direction is positive, which direction is negative. Okay, there was one more question we were asked. I've already forgotten what it is, and I'll try and get to it. Okay. What's the ball's velocity on hitting the ground? Okay, what's the ball's velocity that instant, that moment before it strikes the ground? Now, the ball's velocity, the moment or the instant before it strikes the ground, its velocity has a horizontal component and it has a vertical component to it. So it's traveling both downwards and left to right. And so the velocity vector is a vector that isn't simply pointing horizontally or vertically, it's pointing both downwards and towards the right. And what we're going to do is first figure out that final velocity vector in x and y component language by figuring out the final x component of the velocity, final y component of the velocity, and then we're going to figure out the magnitude and direction of that vector. And so that's what I'm doing in, I call this step one. Here we are. Step one, I'm going to find Vx, Vy, the final x component of the velocity, final y component of the velocity. And then once I figure those, I can worry about the magnitude and direction of the velocity. So for the horizontal component of the velocity, I did that calculation over here. Here's my sketch of the horizontal motion. Here's the red line that represents the horizontal motion of the projectile. I added to the sketch the things that I know. So I know the acceleration is 0. I know it started at 0 meters and went to 0.28 meters. It's a result from the last question. And I know that the initial velocity is 0.6 meters per second. And we're going to find out the final velocity. But that's obvious, actually, if you think about it. If there's no acceleration, the final velocity here must be the same as the initial velocity. And so this is going to be 6.6 meters per second also. Just to be thorough, right, I wrote down the equation that describes that fact. This is an equation of motion that says the final velocity in general is equal to the initial velocity plus acceleration times time. In this case, the acceleration is 0. So the second piece on the right goes away, vanishes, and the final velocity, Vx, is simply equal to the initial velocity, V naught x. And so this just proves through the equation what our intuition told us, that the final velocity is equal to the initial velocity, 0.6 meters per second, because there's no acceleration. So that was really easy. I like that one. Okay, what about the vertical motion? Slightly more complicated, but not too much. Again, I started by drawing a little sketch of what's going on vertically. So in red here is the vertical motion, this straight line vertical motion. And I added to the sketch all the things I now know. I know the initial location y naught, the final location y. I know the acceleration of gravity. I know the initial velocity was 0. I know the elapsed time, 0.47 seconds. Really, the only thing I don't know about that vertical motion is that final velocity. And so I just applied the same equation that I used for the horizontal motion for the final velocity to the vertical motion for the final velocity. That Vy now, the vertical final velocity, is equal to V naught y, the initial vertical velocity, plus that term acceleration times time. The difference is that this is now the acceleration in the vertical direction, AY, that's the acceleration of gravity. Over here on the right, this was the acceleration in the horizontal direction. That was the 0 horizontal acceleration. Anyway, so I plug in the numbers. In this case, it's actually the first term that goes away because the object had 0 vertical velocity to begin with. And so the final velocity of the body is just the acceleration in the vertical direction times the elapsed time. 9.8 meters per second squared times half a second, roughly. That gives you this speed here, 4.6 meters per second. And so here is the answer about what is the final velocity of the ball that moment it strikes the ground in X and Y component language. So that there's a X component, 0.6 meters per second. There's a Y component, 4.6 meters per second. So it's mostly traveling downwards. It's horizontally traveling a smaller amount. Now, that's the answer for the final velocity in X and Y component language. Let me finally calculate it in magnitude and direction language. And so that's what I'll do in this last step here. Now I know the X and Y components. We've just worked them out. I'm going to find the magnitude and direction. And to do that, I'll go through this pretty quickly. I'm just going to use some basic trigonometry of right-angled triangles. So look at this guy here. It's a right-angled triangle. The horizontal side is the horizontal component of the velocity just before it strikes the ground. The vertical side is the vertical component of the velocity just before it strikes the ground. And then the hypotenuse here, opposite the right angle sit in this corner. That's the velocity vector itself. And so if we know the adjacent and the opposite of the triangle, we can figure the hypotenuse of the triangle, its length and its angle, its direction here. And that's all we're doing here. Finding the magnitude and direction of a vector from the X and Y components of the vector is just a bit of Pythagoras theorem and trigonometry of a right-angled triangle. So for the magnitude of the velocity, we just got to, by Pythagoras, take the square root of the sum of the squares of the horizontal vertical components. We know those. So that's the square root of 4.6 squared plus 0.6 squared comes out to be this number here, 4.68 meters per second. That's the magnitude of the vertical velocity. Sorry, that's the magnitude of the final velocity. And then if we want the direction, so I'm going to work the direction here, the direction below the horizontal. But when I find the direction below the horizontal, it's a matter of finding this angle theta. And for this angle theta, the horizontal velocity is the adjacent to the angle. The vertical velocity is the opposite to the angle. So if I want theta, it's going to be inverse tangent or arctangent. If you're old, you use arctangent. If you're young, you use inverse tangent. It's the inverse tangent of the ratio of the opposite side. So here, the y component is the opposite side over the adjacent side. Here, the x component is the adjacent side. So it's arctangent, inverse tangent of 4.6 over 0.6 comes out to be this number here, 83 degrees. So the final velocity in X and Y component in magnitude and direction form is 4.7 meters per second at 83 degrees below the horizontal. And so that's I think of solving that, right, as kind of a crowning glory, a momentous achievement of understanding projectile motion in terms of the horizontal, vertical components of the projectile motion. So it's really, think about, step back from this. This is a sophisticated problem. This projectile underwent this complicated curved path towards the ground. But we figured out how long it took, how far it went, and even the velocity that it strikes the ground with. That's a really big achievement, I think. Proud of myself. Okay. Let's clear this mess up. And let's get on to the next slide. I have no clue what it is now. Oh yeah, this is a This is a good demonstration. It's mildly politically incorrect now, I would say. But what we're going to do is imagine a hunter and imagine the hunter hunting a monkey, and the hunter sees the monkey in a tree. And that's what's depicted in this little picture down below. Here's the evil hunter. And upstairs here in the tree is the innocent monkey. And the hunter is going to fire the gun directly at the monkey. The monkey hears the gun fired and drops from the tree. And we're going to figure out whether the bullet will hit the monkey or not hit the monkey, given that the monkey is falling after the gunshot, but also we have to remember the bullet is falling after the gunshot. If you think about this problem from the perspective of falling bodies and projectiles, the monkey is a simple falling body, falling in a straight line, so that we understood a few classes ago. And the bullet is a projectile. It's moving in two dimensions, left and right, and up and down. And that's the topic of today's class. So the question is, will the bullet strike the monkey? And actually, ultimately, we're gonna explore at what time would the bullet strike the monkey if the bullet did strike the monkey. So we're going to actually answer that question. But I'm going to show you this as a demonstration. We do have a monkey and we do have a hunter. So let me stop sharing this screen. And hopefully now you can see another screen with this video. So this is the Chem Phys lecture room before it got renovated. And we're going to play this movie of shooting the monkey. Now, let me just explain a few things. The gun for shooting the monkey is over here on the sort of bottom left-hand side. And the monkey in the tree will be up here in the top right-hand side. Now, just to be clear, it's not a real monkey. It's a toy monkey. And to hold it in the tree, we're going to use a magnet, electromagnet. And that magnet will be switched off when we fire the gun. So the monkey will drop from the tree when we fire the gun. So there's the monkey being placed in the tree, and it's held there by an electromagnet. And this is me on the left. I'm going to shoot the monkey. And so I'm inserting the bullet. And I shot the monkey. Now we're going to see that played in slow motion so you can see what was going on. Okay, so that's shooting the monkey demonstration. And as you saw in that demonstration, the monkey got hit. The gun was pointing towards the monkey in the tree, The monkey released from the tree when the monkey had the gunshot. The monkey fell, but also the bullet fell, and the bullet struck the monkey. And we're going to try and understand that motion and figure out actually the time that the monkey was struck by the bullet. So I'm going to go back to my slides. I'm capable. And so here we are. And let's try and understand the situation. And the way I'm going to try and understand the situation is by thinking about actually two situations. Firstly, I'm going to imagine what happens in the shoot the monkey demonstration if we were somehow able to magically turn off gravity. What would it look like? And then I'm going to imagine what happens in the shoot the monkey demonstration when gravity is on. And I think that will help us by picturing what happens with and without gravity. It'll help us understand the projectile and the falling body motion that's happening here. So I want to get my drawing pad back up. And so this is the case without gravity. This is what I'm picturing here. And on this diagram, I've got on the bottom left, this is where the gun is. And on the top right, this is where the monkey is in the tree. And I've marked some distances and the initial velocity vector. So this distance, x minus x naught, is that I measured it from the video. It's 25 meters horizontally from the location of the gun to the location of the tree. And then it's 15 meters vertically from the base of the tree to the location of the monkey here. So this horizontal vertical displacement tell me the position of the monkey with respect to the position of the gun. And then the bullet is fired with a speed of 30 meters per second at an angle of 31 degrees above the horizontal. That's the information about the bullet being fired. Now, what happens if there is no gravity? If there is no gravity, okay, the gun's fired, the monkey releases the hold on the tree, what happens? If there's no gravity, actually the monkey doesn't fall. The monkey just floats there. And if there's no gravity, the fired bullet also doesn't fall. And so if there's no gravity, the monkey remains stationary and the bullet just continues on with the velocity that it initially had in a straight line path. And so that's what I'm trying to show here. This dot is meant to indicate upstairs here that the monkey just remains at this location. And this straight line here is meant to indicate that the bullet just continues along this straight line path. There's no accelerations of gravity here. And so in this case, as long as we aimed in the right direction, depending on the speed, the monkey is hit, and the time that the monkey is hit depends on how big or small the speed is. And so without gravity, this is a simple problem of straight line motion of the bullet to the stationary monkey. So that's sort of a baseline for seeing what happens when we switch on gravity, when we turn on gravity. So let's see what happens when we turn on gravity. I mean, if we could do this, turn it on and off, that would be fantastic. But we can't do it, but we can do it in the slides, obviously. Okay, so here's the case now where I've switched gravity back on. The monkey, again, starts in the tree, and the bullet starts from the gun. And the bullet is fired. Here's the direction, 31 degrees, and speed, 30 meters per second for the bullet when it's first fired. And here's the location of the monkey. It's horizontally towards the right, 25 meters, upwards 15 meters. That's its location in the tree. And then this time, when the bullet is fired, when the monkey releases his grip, her grip, both the bullet and the monkey are going to fall. And this red line represents the falling motion of the monkey. This magenta line represents the falling motion. You see it, falling motion of the bullet. And now the monkey is simple falling motion, one-dimensional motion, but the bullet now is more complicated projectile motion. And what we saw was that they both fall the same amount. And so if you pointed the gun at the monkey and the monkey released his or her grip when you fired the gun, both the monkey and the projectile fall the same amount, just like that very first demonstration on the platform of the drop body and the push body. They both fall the same amount, and so they're both going to fall the same distance from the trajectories without gravity. And so if they were going to hit without gravity, they're still going to hit with gravity. And so that's what we see here. And that's what we saw in the demonstration. To kind of prove our understanding, let's try and answer this question. Okay, so we're watching the demonstration. We've seen that evil hunter shoot the poor innocent monkey. And we're going to calculate at what time the monkey was hit after the gun was fired. Now, this sounds like, my first reaction to this sounds like a horribly difficult problem. Why is it horribly difficult? Well, we've got two motion going on, two types of motion. We've got falling body motion of the monkey in red. We got the projectile motion of the bullet in magenta. And we've got to find out what time these two motions cross one another, intercept one another here. It seems horribly difficult. But actually, if you approach it the right way, it's not horribly difficult. If you approach it from our understanding of projectile motion in terms of this sort of underlying simplicity of horizontal and vertical motion under zero acceleration and under acceleration of gravity, we can solve this problem really, really quickly. And so the way to do it, the trick to do it, is to consider, there's two things I'm going to do here. I'm going to consider firstly the bullet and not worry about the monkey. I'm just trying to get the pen back, sorry. So look here, I'm going to consider the motion of the bullet, and specifically I'm going to consider the horizontal motion of the bullet. So firstly, I'm not worrying about the monkey right now. And secondly, I'm not worrying about anybody's vertical motion right now. I'm just thinking about bullet horizontal motion. And the thing about that is, I know horizontally that the bullet travels from over here on the left to over here on the right, 25 meters. And I know the speed, or at least it's easy for me to work out the speed of the bullet in the horizontal direction. It would be the component of this horizontal component of this velocity vector triangle. And so if you know the speed and the distance, it's easy to figure the time. And so that's what I'm going to do. Okay, so here I've drawn the horizontal motion of the bullet from left to right. And on that drawing, I've labeled all the things I know about the vertical motion of the bullet from left to right. And so the black arrow here is the bullet traveling left to right. And I've annotated that with these things that I know. So I know it travels 25 meters. So I called the initial location 0, final location is 25 meters. I know the initial horizontal velocity. Look at this right angle triangle here. this velocity vector triangle here. The magnitude, the hypotenuse is 30 meters per second. The angle in this corner is 31 degrees. The horizontal component is the adjacent. So 30 meters per second times the cosine of 31 degrees is 25.7 meters per second. That's the horizontal motion, horizontal velocity of the bullet. And because there's no acceleration, that's also the final velocity of the bullet. So that's very simple horizontal bullet motion. Well, if I know this velocity and I know the distance I'm going to travel, it's straightforward to figure the time it takes. So that's what I did on the right. Here it is. I went back to my friends, the equations of motion. Here's the equation of motion for the displacement in terms of your initial velocity and your acceleration. In our case, this equation is even simpler because this second piece for horizontal motion goes away. There is no horizontal acceleration. The displacement is just the horizontal velocity times the elapsed time. I can rearrange it for the elapsed time. The elapsed time is the displacement divided by the velocity. Displacement was 25 meters. Velocity was 25.7 meters per second. It was 1 second, a few hundredths of a second under 1 second, 0.97 seconds after the gunshot that the monkey was hit here. That sounded like a tough problem to solve. Turns out it's not a tough problem to solve when you think about it the right way. We thought about it in regards to the bullet's motion and in particular the horizontal motion of the bullet. So again, I think that's a big achievement to be able to understand and solve a problem like that. Let's clear up this mess. Oh, yeah. And next slide. Okay. So next slide is our final topic. And it's an interesting one because it asks that important military question that we initially discussed, which is, if you fire a cannonball, what is the range of the cannonball? Can I fire a cannonball to hit the castle? Can I fire a cannonball to hit the ship? So that's an important military question. And Galileo's understanding of projectile motion gave us the answers to this important question. Now, the next slide, I'm going to show you an equation for the range of the projectile. So this quantity x on this slide, this is the range. We want to know this range, and we want to know it in terms of this initial velocity or speed and this angle here. So we want x as a function of v naught and theta. V naught and theta are the things that you can change. You can change the angle of the cannon, you can change the speed that you blast the cannonball at, and you want to know how far it's going to go. And in the next slide, I'm going to show you the equation, and it's simply based on our understanding of projectile motion and our understanding in terms of horizontal and vertical components. So here's the derivation of the range in terms of the initial velocity and the angle, the direction of the projectile. And let me get the drawing pad back. This is downstairs here. This is the equation for the range. So this is the important thing. This is important. If you were a general in the Welsh Army, right? You want to know this equation. If you were an admiral in the Welsh Army, you want to know this equation. This tells you the range of the cannonball when you try and fire it at the ship or the castle in terms of the initial speed of the cannonball, how fast you fired it at, v naught, and the angle. This theta here is the angle that you fired it at. That's theta. And so, you know, you could adjust the range by firing at different speeds, firing at different angles. Now, I'm not going to go into the details here. If you're, you know, inclined, you can look back at this. I derived this equation. I derived this equation by thinking about a combination of the vertical motion of the cannonball to figure out the time that it's in the air for, and the horizontal motion of the cannonball to figure out the range of the cannonball. And then I basically stuck the time from the vertical motion into the range for the horizontal motion, and that gives you this equation here. We don't need to go through the details right now of the derivation, but just get the fact that the derivation is based on these two guys with their horizontal and vertical glasses, seeing the horizontal and vertical motion, the vertical motion telling you the time the cannonball's in the air, the horizontal motion then telling you the range because you know the time. So that's a masterpiece of understanding projectile motion that gives this simple equation here. I want to make a couple of comments about it. So, you know, the derivation of the equation is interesting. I mean, mildly interesting, I guess. Some of the content of the equation is very interesting, especially if you're, you know, the Welsh general or the Welsh admiral or whatever. So it tells you a few interesting things, and let me make some remarks on them. Inside here is this interesting trigonometric function, sine of twice the angle that you fired the thing at, fired the cannonball at, fired the basketball at, or kicked the football at, twice the angle. Now, if you remember the sine function, so I sort of remember the sine function. If the angle is small, like 1 degree, then sine is going to be I can't remember the sine function. Sine is going to be small too. So when the argument in the sine function is close to 0 degrees, then the sine function is vanishingly small. When the argument in the sine function is near 90 degrees, then the sine function is 1. It's near its maximum value. And then if you went to where the argument in the sine function is 180 degrees, well, again there, like 0 degrees, the sine function becomes really small. And so we can use that understanding of the sine function to understand how the projectile range depends on the angle that you fire the cannonball at. And I've written down 3 cases here. If you fire it at a small angle, so 1 degree above the horizontal, say, then this sine function is going to be tiny, and the projectile is not going to go very far. You've got this sort of path here. And if you want to understand that, well, you've thrown it at such a shallow angle, the projectile quickly comes back to the ground, quickly comes back to Earth and doesn't go anywhere. What about really large angle? If you fire it at near 90 degrees, well, twice of 90 degrees is going to be near 180 degrees. So also you get a very small range. And that's not because the projectile doesn't stay in the air for long. It does stay in the air for a long time, but you're going to fire it and it's going to come down on your feet, which isn't any good. So you don't want to fire it at a large angle either, or a small angle. To make it go as far as possible, the best compromise is 45 degrees. If it's 45 degrees, then 245 degrees is 90 degrees. You've made the sine function as big as possible. Then you're sort of finding the compromise between keeping the projectile in the air for a long time, but also it traveling a large distance from left to right. And that's this path down here. So you might have found this out if you're a general or an admiral experimentally, But Galileo's theory of projectile motion says 45 degrees to fire the cannonball as far as possible. Okay, so in comparing the green projectile and the red projectile, the way to think about it is just think about the vertical motion. If you just think about the vertical motion, the green one is an object that's thrown high in the air and falls back down. The red one's an object that's thrown relatively low height in the air and falls back down. When you throw something high in the air and it comes back down, it's going to be in the air longer. When you throw something not very high in the air and it comes back down, it's not going to be in the air so long. And so the green one has taken longer to reach the same range as the red one. And it's taken longer because it's gone higher and it takes more time to go higher. The red one has taken less time because it went less high and it takes less time to go less high. So that's the answer. That's the answer to that problem. The times are not the same. The ranges are the same, but other things like the initial velocities, the initial directions, and the durations of the flights, they're not the same. Only the range was the same. Okay, well, that's the end of today's class. Next class, we're going to move on to Newton's laws of motion. So I'll